great pleasure to welcome Pieter Kok, who is going to talk about open problems in noisy quantum metrology.
Thank you very much. Thank you very much for inviting me. It's been a pleasure being here. And I decided, being inspired by some of the earlier talks, to do a tutorial because the terminology Fisher information and Kramer-Rao bounds and quantum Kramer-Rao bounds and quantum Fisher information have been used, and I'm not entirely convinced that everybody is fully conversant in those. So I know a little bit about it. So therefore, I thought I'd give you my perspective of where these terms come from, and then that leads me into the possibility of talking about what open problems are there in quantum metrology. So we start in the classical case. So classical metrology, and I have a family of probability distributions that form a surface, a hypersurface called the probability simplex. So the easiest way to get an intuitive feel for this is to look at a system with three possible measurement outcomes, which I can draw in 3 dimensions. So I have probability of outcome 1 is measured by P1, P2 and P3, and then the probability simplex is given by the normalization that P1 plus P2 plus P3 is equal to 1. And that's this triangle. And then the main question that I'm going to ask throughout this is, if I have 2 probability distributions, column A and B, how many times do I have to interrogate the system in order to tell the difference, in order to tell whether my system behaves according to probability distribution A or probability distribution B? And in order to make life a little bit easier, interesting, I'm going to assume that there's some kind of process that is parameterized by theta that takes me through A and B. And I want to estimate theta. So that is our main objective. Okay, so and then the other thing we can say, we can rephrase this in saying how big must this length theta be in order to tell the difference, because there will be regions of uncertainty for any finite number of samplings around, so what you can say about where you are in this probability simplex. So the way to attack this problem is to have a look at a metric on this space. So that's what we're going to do. We're going to derive a metric based on what we know about statistics and probability. So we know formally what a metric looks like. We write it in infinitesimal form. Our coordinates are our probabilities. So these are our contravariant vectors, and we have a metric tensor G, J and K, dpj and dpk, and I sum over J and K. I make a distinction between the contravariant and the covariant because that's important. And so what I need to do now is to find what is the metric tensor that describes a distance on the probability simplex that gives us a natural distance measure for statistics. So the way to start with this is to look at a natural inner product, and the natural inner product we can take as the expectation value. So if I have some random variable A, the expectation value is given by sum over j, aj, pj. And the random variables A actually form a covariant vector field, and this is because the surfaces, or rather the collection of expectation values with the same expectation value forms surfaces in the simplex. So you have a nice graduated expectation values, and so you can create stack vectors and whatnot. So it's covariant. And in order to create the metric, we need, well, this is not enough to find out what our metric tensor G is going to be. We need a two form. So we need to look at two covariant vectors, and so what we can look at instead, is the correlation. And because when we look at the correlation, we can write this formally as right. So that's our two form that leads to our that uses our metric tensor. But I've already used the term correlation. This is also in statistics a regular correlation, which we know how to calculate. So this we get from differential geometry, and this we get from statistics. And we now say, well, we're looking for a particular distance or a particular metric in our probability simplex. And so the natural one would be to equate these, which I've already done. Oop. Not sure what happened to the light there, but there we go. So that means that we can identify the contravariant form of the metric with the this guy, and then of course we need a k there, so we need a Kronecker delta. Now I forgot to mention that when you have a metric, this is the inverse of this guy. So because this is the contravariant one, and we need the covariant one for our distance on the probability metric simplex, and therefore, well, we solve this to get, and note that we're not using summation convention here. So this is what we. Oops, excuse me about that. This is what we have, and then we substitute this back into our statistical distance, and we find that this is the distance measure on our simplex. And you see that this is not a Euclidean distance. In fact, it's
Excuse me,
yes.
why is that?
Why is this?
Yeah.
Because KL is delta JL. So this is the Kronecker delta, and so this is yeah. Okay. So so we have actually rather a strong curvature in the probability simplex, because as you can see, if we're getting close to the edges here, then this distance blows up. So I think I want to come back to that in. No, that's fine. So if I have, let's say, a probability distribution here, and I want to look at the distance between A and, let's call it C, then the question was, how many times do I have to sample the system in order to tell the difference between A and C? That was the original question. And you see that if we find a measurement outcome where P1, so P1 is the probability of measurement outcome, let's say X1. If we find X1, we know immediately that it has to be A. Because it cannot be C, because C has probability 0 for outcome 1, right? So you have to do only a single measurement, and you know with certainty that you have a probability distribution A. And that's why the distance in your probability space is infinite, because you get with a single sample, you get an infinite amount of information.
On average, or?
Yes, it's on average. Yeah, because you may not actually get P1 after all. Yeah. Okay, so, and I want to make an aside. And remember that this is entirely classical. If I take dpj as if I take the probability as the square of a probability amplitude, then ds squared, my infinitesimal distance, is given by this. It's relatively easy to check, and you see that now this is a Euclidean space. And so I've not done any quantum mechanics, but somehow we get probability amplitudes. If we go to probability amplitudes, we get a completely flat space. Okay, so that's an aside. I'm not going to use any of that. Well, I'm not going to use this. I'm going to use the rest. Okay, so we have a distance, and then we want to see. Okay, we are interested in the distance along this line parametrized by theta. So we want to know what is ds along d theta. And for that, is it this one? For that, we can take the derivative. Divide ds squared by d theta squared. We use the expression that we have. So this is so that's I've just plugged in ds squared here, and I can rewrite this sum over j as pj d ln pj d theta squared. And this is, well, s is a distance and theta is a particular path. We can think of this as, could be time. So this is some kind of velocity through our probability simplex squared. And this is a very important quantity, because the faster you go through your probability simplex, the quicker you would imagine you'd be able to distinguish between A and B. So this is a quantity that is of importance, and this is called f, and particularly f of theta, and this is the Fisher information. You see the Fisher information appear in both forms, I would say equally likely. This is quite nice because now here we have what's called the logarithmic derivative, which also appears in the quantum version, and so it's the average over the logarithmic derivative. So it's a pretty nonlinear thing, which is the cause of some trouble down the line. But this is the Fisher information, and you can think of it as the amount of information that you get about your parameter theta in a single measurement, the average amount of information. So the average amount of information about theta in a single measurement.
Why do you do the theta squared?
Oh, because if I do ds squared over d theta, well, I can't interpret it as a nice velocity. Yeah, it's so in some sense this is just, you know, juggling symbols. But and I should really mention that these are not rigorous proofs, but to me they're the more intuitive way of looking at it. Okay, so how am I going to push this one up? There we go. Right, so so then we have the Fisher information, and but we have only infinitesimal distances in the simplex, and of course we want to know about finite distances. So for that we're going to use do a Taylor expansion. So we're looking at, let's suppose that theta is in general an affine parameter, so we can choose theta equals 0 at A and then theta equals some other value at B. And so let's call that some small amount of movement along the path. And we can write this.
Can I ask a question now?
Yeah.
So that derivative there, so is it like you can really interpret it into operationally in terms of bits and bit rates?
That is a good question that I have to think about that. Because I think that is not necessarily known. But if anybody else feels differently, feel free to jump in here. So what I want to do now is look at the amount of distance I make through the simplex as I go an amount delta theta through my parameter. And to do this, I just use a simple Taylor expansion to first order. And then, of course, I have ds d theta at theta equals 0. And from that, I'm going to rearrange and say delta s is s of delta theta minus s0, so that's the definition. And then I'm getting delta s equals delta theta, and now you see that this is the square root of the Fisher information. So I'm just going to put that in there with the understanding that in our case here it's theta equals 0, but in principle you can shift this whole thing. So now I'm going to make a shortcut to the Kramer-Rao bound, because so what do I want to do? I want I want to know how many times, I'm coming back to this original question, how many times do I need to sample, do I need to interrogate the system in order to tell the difference between A and B? Well, this is a dimensionless number, so n times this small distance should be greater or equal than 1, because it's all dimensionless. So 0, well, that's always going to be the case, but except if n equals 0. But so I need to put in some non-zero constant in a dimensionless system. So I choose 1. Right? This is a certain arbitrariness that comes from the fact that when you're dealing with probability distributions, there is always some fuzziness. And from that, I can now say, let's divide by d theta, because we assume that that's not 0, so we can do that. Then we use this relation here, and we can rewrite d theta must be greater or equal than 1 over, I forgot a square here, so what I want to do is this, sorry about that, so now this is just f, and this is the Kramer-Rao bound. So that is the classical estimation problem. And now we're going to do the same, more or less, well, it's going to be completely different, but for quantum. But it's going to be very similar. We're going to try and create a metric, and immediately we find that we run into trouble. Speaking of trouble, I think I need to speed up considerably. In the quantum case, so we started with an expectation value, and in the quantum case, of course, we have a self-adjoint observable that is its expectation value is related to the trace of density operator. Well, you know this well, and then we want to look at the correlation. And now the problem arises because this may not be, A and B are self-adjoint operators, but the product of A and B may not be self-adjoint. So may not be equal to AB, because when you go through this, you get B dagger, A dagger, BA, but BA is not necessarily the same as AB. And that means that we need to fix this, and we find, so instead, we are going to symmetrize this thing, because when you take the anti-commutator of A and B, then that will be self-adjoint. And because we want the autocorrelation to remain the same, we put a factor of 1/2 in there. And so we use this, which is 1/2 trace rho AB. And I'm arguing by analogy now, but this was I think this was done by Brownstein and Caves, and this is they do it sort of rigorously, so I'm going to rewrite this as so if I can rewrite this thing as by using the cyclic property of the trace as a rho anti-commutator with B. Right? So this is not difficult to show. And this is analogous to what we had before, where we had AJ, BJ, G, JK. Right, so that was the classical version. So I'm going to say, yeah, this is trace of A, and then some super operator row of B. So these are operators, and I call this R because this. So what does G do to vectors in geometry? Well, it raises the index from a lower covariant form to an upper contravariant form. So this is a raising operator. Not raising in terms of ladder operators, but in terms of the covariance and contravariance of the vectors. And so remember that we needed to get this thing down, so we needed to look at the inverse of this guy. So we need to look at the inverse of this operator. So the inverse of R, no, that's, I think we have, well, we'll call it L, because that would be the lowering operator. Right? And so I think I'm going to just say what it is, because, well, there's two forms. So first of all, L row of B can be written in the eigenbasis of rho as sum over jk 2bjk over pj plus pk jk in the eigenbasis of rho. Right? That's, if it's not in an eigenbasis, it's getting a little bit more complicated. The other form is implicit. So when B is rho prime, which is d rho d theta, there's another form for L that is used a lot, and that is rho prime equals 1/2 L rho. So this is not acting on, but this rho. So it's an anti-commutator. Right. And yeah, so if you want to get the mathematically rigorous form of this, go to Holevo's book, because he does it sort of all very carefully. So now again, what we can do is, I'm now putting a row so that we know we're talking about distances in the quantum mechanical state space. And we again want, well, basically, we want this, d rho, L rho, d rho. Right? So, and this is the exact analog of the classical version, which was, well, it's implicit up there. And so you have your two, so classically these would be your dp's, and this is your lowering, your metric in the classical case. And this thing, this thing leads to the following. We do the exact same thing again. We divide this distance by the d theta squared. It's rho, not phi. And so, because these are just small numbers, we can bring them inside the trace. We can bring them inside L, and we have rho prime, L rho, rho prime. Now you see why I was looking at this special case where B equals rho prime, and this is the quantum Fisher information. So what is the quantum fish information? Oh, first of all, ds squared sub rho is the Buress metric on the quantum state space. So it's Riemannian, which is how we started out. So it's got nice properties in that regard, and so now we have a completely different quantity from the classical Fisher information. So the classical Fisher information depends on the probability distribution. So that means we have a state preparation, we have some kind of evolution that puts theta in your state, and then we have a measurement, and that measurement leads to a probability distribution. And for that probability distribution, we can calculate the Fisher information. But if you look at the quantum Fisher information, you see that the measurement is absent. It is all about the quantum state, rho, and its derivative. So there's no measurement in there. And this tells you, and this is in fact true, but sort of intuitively this tells you that the quantum Fisher information is the amount of information about theta that's actually in the state. Now you can have information about theta in your quantum state, and then do a very stupid measurement and get no information about theta in your probability distribution. So your classical Fisher information would be 0. So the quantum Fisher information is actually the upper bound of the information. It's the for an ideal measurement. So it's the information you get in an ideal measurement. And then we can do the same argument. To make the same argument that we did to get the Kramer-Rao bound to get the quantum Kramer-Rao bound. So it's just replacing the classical Fisher information with the quantum Fisher information, and so this is the quantum Kramer-Rao bound. And so because FQ is not actually related to an actual measurement, this is a fundamental bound of nature. So whatever you do, whatever you measure, you never can get a precision in theta better than this. And now I snuck into an interpretation of d theta that I haven't commented on before, but when you do things carefully, then delta theta here is, or rather delta theta squared, is the mean square error. And this bound, and the regular Kramer-Rao bound is saturated asymptotically, so for large n, in a maximum likelihood estimation protocol. So you can reach it, but this should only be taken seriously for large n. Okay, so any questions so far? Yes.
Can I, because the symbology is so different, can I see how, say, for a maximally mixed state, that the quantum Fisher information reduces the classical one?
For a maximally mixed state?
For example,
No, for a maximally mixed state, so no, you can't. No, you can't just sort of take a particular state and sort of reduce it to the classical Fisher information, because you need to put a measurement in there. Mm-hmm. And so this is fundamentally not dependent on what kind of measurement you do. So what you can do is optimize overall possible measurements the classical Fisher information, and then you'll find that you get this. So it's, but you see, this is an.
What do you optimize?
Okay, so you have your Fisher information, which tells you how much information on average you get out of your measurement, and so different measurements will give you different amounts of information, and so you have to find the one that gives you the most, and that one will coincide with this guy. And so it's an optimization problem, which is a pain. So now this is a closed form, which is not due to an optimization. I derived it in a different way. Yeah, but these are two different ways of looking at it. Right, so then it's fun to have something like this, but as you were already alluding to, what on earth is this? So we would like to be able to say a little bit more about that without having to go through these crazy super operators. And so luckily we can say more about this. Because, well, we have the derivative of rho in there, and we know that the theta, is by some generalized von Neumann equation given by this, where G is the generator of translations in theta. So, for example, you could say u theta is e to the minus I over h bar g theta. Right. So if this were time, then this would be the regular Hamiltonian. And now we notice, because of the special property of the commutator, that we could also, instead of using G, use delta G, with delta G is G minus the expectation value of G. Because this is just a number, so it is completely unaffected, or it does not affect the value of the commutator. And when we do that, we're going to get delta G's in there. And I'm going to skip this in the interest of time, but when you do that, we find that FQ is smaller or equal 4h bar squared delta G squared. Some people call this the quantum Fisher information, but this is a bound, right, on the quantum Fisher information. This is the fundamental form of it, and the equality is true for pure states. So if you start with a pure state, then you'll find that the quantum Fisher information is in fact the variance of your generator of translations. So that is nice, because that's actually something that you can often calculate, and so this is how people come up with bounds on metrology. Okay, so now I would like to say a few things about metrology, because and I'll do that over here, because we often sort of have two different types of metrology in mind, sort of classical metrology and quantum metrology. And you can see from, let's take this one. If you take a particular measurement of a system to find some information about theta, then you get a certain amount of information, and that will be on the order of 1, let's say. It doesn't really matter. And then when you repeat that experiment n times, so we assume that these are independent experiments, so the state preparation is independent and whatnot, then you see that you go with a, you scale with or rather your error scales with 1 over the root of the number of trials, right? So this is exactly what you know from classical measurement theory. So this goes with 1 over root n, and this is called the standard quantum limit. Alternatively, so this crucially is n measurements. Alternatively, you can take all your resources, these n measurements, and use them up all at once. That's the usual way people think about it. And so let's append this with SQL. So this is sort of measurement type 1, and then measurement type 2 is where you take you do a single measurement and you take all the so for example, when you have a large GHZ state or a Noon state, so some large entangled state, and you have some kind of resource count, which I'm getting to, then what you can have is that f can be proportional to some other number m squared, right? And n equals 1. And then what we find is that delta theta is greater or equal than 1 over m. Yeah? And this is called the Heisenberg limit. So I append this with HL. And why did I choose m instead of n? Because typically people call this n, and then so f is goes with n squared, and then people say, okay, the Heisenberg limit beats the standard quantum limit, and that's true for a large number of cases, but not in general. And so this is yeah. So then another thing to note is that here we do n measurements. So if you want to know a numerical value of theta, then you can get, well, up to, what is it, log 2 of n, log 10 of n bits of a numerical value with some kind of error on theta. And here you only have a single bit of information. Right? Well, okay, it doesn't have to be a bit, but usually when we talk about qubits that are entangled, yes, you get just a single measurement outcome out of 2, so it's a single bit of information. So basically that's the answer to a yes-no question. So is the effect there or is it not there? And the precision then means that you can the effect can be sort of closer and closer together, and you can tell the difference between them. But it's not the same as this situation. And in practice, you will always have to, if you're interested in the actual numerical value, you will always have to do multiple measurements. Or you need a lot of prior information. You know it's either there or not there, and but you already know that if it's there, it has this particular value. Okay, so then I want to say a little bit more about these resources, because it's sort of rather important, and it is at the heart of many claims of beating the Heisenberg limit, which I think these claims are unwarranted. So I have to be careful with how I phrase these things, since this is going out in public. So basically, let's suppose that we have n individual probes. So these horizontal lines are physical systems. They get, well, let's say a phase gets imparted on them, this theta, and we want to estimate this. And so now here we do n of them in parallel, because it doesn't matter if you do them in series or in parallel. And then what we get is n samples. And now, what is the resource here? Well, the resource really is the number of times you probe your system. So every time I have a box here, you probe the system. And so you can take a similar, so it looks exactly the same, except that, so this is different way of doing it. So you send in instead one single entangled state, and you do some measurement at the end. So here we have so f equals 1 for each one of these, and here we probe n times again. So, but now, because we do this once, here n equals 1 and m equals n. So indeed, you get the 1 over root n versus the 1 over n sort of speed up in metrology. But that is a simple case, and then people just came up with an alternative that said, let's look at a situation like this. I think I'll stick with 3. No, 3 is not good. I need to go to 4. No. And finally, this guy. Okay, so here we have n physical systems, and they go through. Well, how many times are the systems probed here? Exactly. So, well, what is a probe is the question. Well, the probe here is a pair because we have used, so j greater than k, gj, gk, right? So j and k indicate these lines. And so the number of probes m is 1/2 n times n minus 1. And you see that indeed, as somebody said, there's 6. 1, 2, 3, 4, 5, 6. Right. And now when I calculate, so I send some massively entangled state through here, I can get the situation where, so this now goes with n to the 4, right? And then people say, ah, look, so because my Fisher information goes with n to the 4, my precision can go with 1 over n squared. And therefore, I've beaten the Heisenberg limit. But this is cheating, and I do say that knowing that I'm going out on the internet. This is cheating, because what you're doing is you're looking at the number of physical systems, but not the number of times you probe the system. You can use a single physical system to probe the same, so this is meaningless. What you want to do is look at how many of these probes there are. And so the way to do that is to look instead, so the resource that you're interested in is instead given by the expectation value of this generator. And there is some debate on whether you should use this guy, but it doesn't really matter for practical purposes. So, so that is the origin of many of the Heisenberg limits beaten claims, and I think those claims that are based on this argument are false and not actually all that useful to bring the debate further or bring our knowledge further. So then
Sorry, so
yeah.
you wanted 4 lines because now you have a different number?
Well, if I use 3
It
lines,
would have been 3 and 3.
yeah, if I have 3 lines, then I have 3 here, and then it's the same. Yeah. So yeah. Okay. So so now in the last 5-10 minutes, I want to get to the open questions because well, in fact, there are two main open questions, and I'm gonna rub out this because It's the front board, which is nice. Okay, so first of all, what, it's not Dutch, what is FQ for noisy systems? And secondly, and this is why I had to actually go quickly through the resource count, can we use error correction? And so the first one is, so what is FQ for noisy systems? Now, when we bounded the quantum Fisher information in terms of the variance of the generator, so FQ for pure states was equal to 4 over h bar squared delta G squared, we assume unitary transformations, and we use the von Neumann form for rho prime, right? So, well, we know how to implement noisy systems. Let's look at this, where now this L is the Lindblad operator, including the unitary part. So, you know, you plug this in to your Fisher information and see what you get. And when you do that, and you don't know anything about the actual, so let's say put it in Krauss representation, and then assume nothing about other than, you know, the standard, you know, must sum up to 1 and that sort of thing. You do that, and you find that you don't know enough about the system to bound it. There is no bound. So you need to actually know a little bit about well, certainly about the interaction that gives you your rotation. Let's assume that that is known, but you have to actually know a little bit more about the Krauss operators in order to bound this. So this by itself formally is not enough. So Sarovar and Milburn they took the Krauss operators and and they found a bound. So they found that it's not equal. So there's some room there, and then let's call it C sub k, which is defined as 4 times the trace of, and this should be, well, I'll put the sum in here, the Krauss operators, J, and this is the derivative with respect to the theta that you're interested in, rho kj dagger, right? So this is what they find, so this could be, in principle, really, really high. Then Escher et al. Tightened this bound, so it's smaller than ck minus, and they added a term that I kj dagger rho k not primed, sum of a j. So this is positive, so this is a tighter bound than this, but it's still not. It's not always tight. So it's not an equality. So this is one open question. So what is a good bound when you have a noisy environment? Then very recently, Alipur et al. They took a completely different route, and they found that the Fisher information, the quantum Fisher information, is right. Yeah, so the noisy one is is given by, so now the tilde here is with the all the Lindblad terms. Without the tilde is with only the Hamiltonian bit. And so this, and there should be a kappa here, with kappa is either 2 for pure states, or 4 lambda max over the purity for mixed states. And now you see immediately that there is a gap, because if you take rho to a pure state, then lambda max becomes 1, the purity becomes 1, and you get 4, whereas for pure states it is 2. So there's a gap there, so it's also not a tight bound.
Sorry, what's the untilted one?
So, okay, so yeah, it's slightly confusing. So the tilde is the Fisher information from, if you take the full noisy evolution. The untilted one, so maybe I should do it the other way around, but the untilted one is when you strip out all the noise and stick only to the, so you'd start with the same input state, but you don't add the noise in the process. That's the difference.
But then you're estimating some parameter in some Hamiltonian there.
Uh,
I don't know, otherwise it won't characterize.
Yeah.
Okay.
Yeah. So so in the Hamiltonian is always there. Yeah. So that's so that's what you get for noisy systems. Then there is a recent result last year by Madeleine that I'm sure he can tell you much more about. That tells you, let's do that in the corner here, that if you want to measure your theta and then your error, if you have noise, will be bounded by this, where these two, epsilon plus and minus, so let's suppose that you have, you're bounded by, your noise can be decomposed into two pure evolutions, and they have, let's call them relative weights, epsilon plus and epsilon minus. Then they show under very general conditions that you're bounded by this. And so you see that if these are constants, then you're going back to the standard quantum limit. Right? So that's a very strong result. And if you want to know more, ask Madeleine. And then finally, in the last minute, I'm going. I'll just say a few words about whether we can use error correction. And the answer is, well, first of all, you may think, no, we can't use error correction because you increase the number of qubits or the number of systems, and then what you do is, well, you have to count that in your n. But that's not the case, because what you're doing is this n here is the number of probes that you're making, so, that you sent into the system. So if you can add extra qubits for error correction, as long as they don't also probe your system, because then they don't count towards. It's a bit like when you run an experiment. Do you count the coffee among the, that keep the graduate students going? Do you count that among your resources? Well, not usually, because once you do that, where do you stop? Right. So this is the same.
Error corrections implies measurements, right?
They do, yeah.
Right. Would you take them into account?
No. Only the system that interacts with the
I get it.
And so what you can do. So there's a couple of papers out this year that actually show that under certain circumstances you can error correction can work, and but the question still is, okay, well, so what's the most general error that you can correct? So basically, what you want to do is get away from this, right? So you want to retain this Heisenberg scaling, and by using error correction that circumvents the assumptions that led to this result, and the answer is that you can, because you can use you can think of error correction in one way as so you have your qubits that don't interact with your system that you want to probe, and the qubits that don't do that, you can keep them very pure through error correction. So you have the idea of an ideal qubit, which you don't normally have in quantum computing error correction. So you have an ideal qubit and a noisy qubit, and once you have that promise, you can actually do quite a few things. So there's a couple of papers by Dorota Harnoff and Michel Lukin and Wolfgang Dürr are the ones that spring to mind. And so they're exploratory. So there's an enormous amount of work to be done here, I think. And then finally, how do you calculate this Fisher information, right? So that's the big question, because that's the hard thing. So with that, I think I should stop. So thank you very much for your attention.
Okay, thanks, Peter. Any questions?
In this expression with the Gauss-maps, it is clear how you optimize over the choice of the Gauss-maps?
No, I forgot to mention this. Yeah, these are optimization problems. So it's maybe in some cases it's easy, but in general, I don't think it is. Yeah, yeah.
You said that if you use entanglement for measurement, you can get more resolution.
If you do it right.
And in your example, you use bipartite entanglement, right? In some sense, because two nodes.
I'm not entirely sure which example you refer to.
Like this.
Oh, right. Yes. In the sort of in the special case of so this would be like nonlinear. So what Akira is referring to is this situation where you have. So I wouldn't call this bipart entanglement, because the entanglement is about the state. This is really about the probe or the.
Okay, not the entanglement.
There could be entanglement in there, or there could not be. It's yeah.
Okay, if there are no further questions, let's thank Peter and also Jason.
I need to wash my hands.